Okay, and for our last presentation of this session, we're going to have Ana-Andreea Stoica talk about fairness rising from the ranks, hits and PageRank on homophilic networks.
Now it should work. Great. So today I'm presenting work, Fairness in Link Analysis Ranking, Hits and PageRank on Homophilic Networks. This is joint work with Nelly Litvak from the Technical University of Eindhoven in the Netherlands and Augustin Chaintreau from Columbia University, my former PhD advisor. The main motivation is for us was to think about that algorithms that use network features may incorporate bias or even amplify bias that you may see in society between different demographics groups, for example. And there's recent work showing that, for example, such algorithms that are used in ranking, for example, in Google search, are subjected to such biases. Recent work have shown that, for example, if you look at the Google search images results among, for example, the top, if you look at like who is the CEO in the US and you look at distribution of gender across Google image results, this is quite biased. If you look at top 100 Google image search results for CEOs, 11% of them are women, although in the US, 27% of them are actually women. So in the meantime, I think Google has updated this and there's follow-up work on that, but it sparked a bunch of work that thought about what exactly causes this kind of issues in the way different groups get represented in ranking. So recent works have shown that, this kind of like, if you think about minority groups in the ranking that, that is outputted by such algorithms, they may get suppressed or, in a sense, pushed down. A recent empirical study was studying this question in the context of different search queries. So if you do a search query for a gender-neutral term, such as person, and if you look at the gender distribution across the Google image search results, you would find certain biases. And that bias correlates with the global gender gap index of the location where you did the search. So in more unequal countries, there's more bias, in a sense, less diversity in the search results, although the query itself was neutral. In more equal countries, by this measure, you would see less or more diverse results in that way. And there's an interesting follow-up that they did in this study. This is by Vlasciano and Amodio, that came to say, like, well, do these results really matter? Like, who will be influenced by these? So they ran an RCT, and they showed this kind of results to a set of to a set of subjects, and then they asked them to decide on a set of job candidates, like, are they qualified, are they not qualified? And what they showed that in their hiring decisions of the subject in this randomized controlled trial, well, the treatment is, do you see more biased results or less biased results? That affected their decision for who should be hired if you look at it, again, by gender. So this kind of representations that we see in ranking have an influence perhaps on what we think further on about like different kind of decisions we may have in real life, and it sparked interest in the community for understanding where these biases come from as well. In our work, we thought about what exactly in the network structures that are present in this kind of ranking algorithms may explain this kind of issues as well. Where is it? Oh, sorry. All right. So we're looking at link analysis ranking algorithms that are used in search results, for example, the PageRank algorithm, as well as hits. Both of these were developed at the same time. One of them took off as a main Google search ranking algorithm. They're quite similar, but they have some fundamental differences, and we're interested in how different network structures may incorporate bias in this kind of algorithms. Both of them use the network structure to create basically a relevancy ranking for search engines. The results that they output may also be used as feature for recommender systems. So in a sense, they're an alternative to think about who is central in a network. Sorry, all right. So in these algorithms that use network as features, what really matters is how well you're connected and who you are connected to. And the more you're connected to, the more relevant you are to begin with. These kind of algorithms were originally developed on networks of web pages that link to each other, so that's kind of the network structure we think about. And the more connected you are to others, the more relevant you are. Of course, you can think about why don't just look at like degree, the number of connection that you have, and these algorithms were developed as an alternative to degree, thinking that just the degree, just your immediate connections do not provide enough information for you being like relevant or very central. So instead of looking at degree, they basically look further than that at random walks in various ways. So we can think about this degree distribution of different nodes in our network as, in a sense, the baseline. You have a population of people, maybe who each of them comes from different groups, here represented as red and blue. Red and blue may be demographic groups, interest group, affiliations, and so on. And if you think about the number of connections that they have, this is, in a sense, what you see in society. Some of them are more connected than others. Here's an example of that would look like if you just rank people or your nodes by their degree. Maybe there's some bias, and maybe there's a societal bias that is, in a sense, our baseline. Under such algorithms, they create a ranking that is trying to do something different, perhaps by looking at random walks, what PageRank does, and so on, and it will create a different ranking. And we're interested in comparing with the baseline. Is the ranking that is outputted more biased than what we've seen in society? Is it mirroring the bias that we see there? We can think about bias as, for example, the representation of different groups in top K. Imagine the Google search results that you see. You're looking at the top page that you from your search query, and you're looking at the distribution among different groups. For example, here, maybe I have more of the group that is blue in some top K ranking as well. So we started by analyzing this on different data sets, by simulating these algorithms, both just looking at the degree, PageRank, hits, and looking at how the representation of different groups appears at different levels of the ranking. So we looked at 3 data sets. For example, we looked at the APS data set. This is the American Physics Society citation data set. The nodes are papers, and the different labels are different subfields in physics. So each paper, there's 2 subfields. One of them is in minority. This is a dashed line, the representation of, say, minority group. In this case, it's 30-something%. Of course, papers that connect more, papers that are in the same field connect more with each other, and we call that homophily. In network science, this is nodes that are more similar to each other tend to connect more. Of course, in the citation networks, you would see that very prevalently. The different lines that you see here is the representation of the minority group on the x-axis among top X% of nodes, and on the y-axis is just the representation of that minority group. Here I'm calling R. Red is just the minority group. Blue is the majority group. And the different colors represent the different ranking scheme. So let's look at degree first in blue. This just represents like what happens in the network itself. The representation of the minority group as you're looking at higher and higher rankings, as we're moving to the right, is dropping from the original ratio, which is the proportional representation ratio, say 30-something%, towards something less than that. So among top 1% in this ranking by degree, perhaps you have something less, you have 20% of the minority group represented. If we're looking at, degree is in orange, I misspoke. All right. If you're looking at this ranking and this representation of minorities by different algorithms, for example, PageRank. PageRank actually improves a little bit of the representation of minority compared to the original degree. So although there's some bias to begin with, they actually improve it. On the opposite end, hits, this alternative algorithm, is actually doing really badly. So the representation of minority actually drops to 0 as you're looking at higher and higher ranks. So we're kind of in this kind of scenario where even in the top 10% of the ranking, we're close to 1% minority representation. We're looking at different data sets with different network structure that will exhibit different kind of behavior. We look at the different citation data set, the DBLP data set. This is a network of computer scientists where the nodes are people, they're authors, and the sensitive attribute here is gender. So we have 2 groups, with minority being women in this data set around 22%. And the edges are citations, so who cites who. And in this network, there's still some level, it's not that much homophily, people kind of cite everyone in some way. And in this data set, basically all algorithms do the same. They're still quite far from this dashed line, which is just a proportional representation the percentage of the minority group in the general population, around 22%. So you still see that there's some bias, and as you look at like higher and higher ranks, their representation still drops. But they're all kind of doing the same. They're all, in a sense, mirroring whatever bias is to begin with. And finally, we looked at a different data set. It's an Instagram data set collected by our lab, where nodes are, again, people. Edges are who likes or comments each other's posts on Instagram. And there is a moderate amount of homophily between two genders. These are the two groups with 45% in the minority. These are actually women in the group. And here we actually see a reverse trend where, the degree ranking is actually biased, is favoring the minority. That effect is amplified by hits and alleviated by PageRank. So in a sense, you see this opposite trend from the original data set. And our main question was to figure out what exactly explains this behavior in algorithms such as PageRank and hits. Our evidence, our work, is finding that we can explain this through network dynamics by using network models. First of all, inequality in the degree distribution leads to bias in ranking algorithms to begin with. And secondly, that homophily among communities can alleviate bias for PageRank, but amplify bias for hits. So we're using network models as a mechanism for explanation, and I'll go quickly over one network model that we found particularly explanatory for us. So we're looking at a model that's called Bias Preferential Attachment Model, proposed in 2015, which has a few main ingredients that I'll go over. First of all, there's two groups, minority and majority. There's nodes, they're either blue or red, and the network increases as we're moving through time. At each point, a new node comes in, and it connects to nodes that exist with preferential attachment, so nodes connect with probability proportional to their degree. This leads to the rich get richer effect, where nodes that are popular become even more popular. And this effect is often observed in online networks, especially documented where you see this power law degree distribution. Finally, there's homophily. If the nodes have different labels and the connection is accepted only with a certain probability, modeling this homophilic behavior that we often see between demographic groups, interest groups, citation networks, and so on. The fact that people connect with people similar to them more. So this model is interesting in a variety of ways. First of all, we can compute its degree distribution as following a power law as well. This is an extension from the classical preferential attachment model in network science. But more than that, because you have two groups and homophily, you have a degree distribution with two different power laws. And the fact that they're different explains why the degree distribution ranking is already biased to begin with, which we notice in all of our data sets. Second of all, we wanted to see, can we use this model to understand our ranking algorithm? So I'll show you a quick example of how we can understand hits. And the main result that I wanted to go over is the following. We have a theory result under which we can say, under this network model, first of all, the average ranking score for hits is lower for a minority group than majority. This is just on average. But further than that, there exists this close-form relationship between homophily, how homophilic the network is, how clustered it is, and how much bias amplification you get as compared to the degree distribution against the minority group. So low homophily networks, maybe bias is just going to get mirrored or reduced compared to the degree distribution. In very homophilic networks, you're going to see this large bias amplification where the minority representation just goes to zero. A quick background on this kind of algorithms on hits is that basically hits does the following. You have a network and you care about who's relevant in the network. And the way you're going to compute that is instead by looking at just your number of connections, you're going to look at your friends of friends. So the more people point to you, the more popular you are. And you can compute that in closed form as the principal eigenvector of the adjacency matrix A of your network, modified in some way. This is also equivalent to counting forward backward paths. And basically, based on our model, we can compute the probability of ending. If you start from a blue node, what's the probability that you end in a red node, through these backward-forward paths, through the model that we have. And this probability basically allows us to compute, on average, what is the centrality score that is ranking with output, that is algorithm with output, as a function of your original in degree, perhaps the out degree as well, and another factor, which we call it some multiplicative factor. So now, if we want to compare how biased your ranking is compared to the original degree distribution, if, for example, you have an out degree that's constant or you know something about the distribution, all you need to know is how this factor works. And our work provides some mean field analysis that allows us to analyze this difference. So for example, if this multiplicative factors would just be like 1 for everyone, you would recover the degree distribution. In more homophilic networks, they actually behave very differently, and then you end up with a very biased degree distribution, with a very biased ranking where the minority nodes would get kind of suppressed, even more so compared to the original degree distribution. In comparison to PageRank, maybe some of you would know, PageRank basically just does like 4 paths. The more you're likely to end up in a node, the more likely you are to be central. By comparison, the HITS algorithm does this backward 4 paths. So there's some similarities and some differences, and this kind of differences really change their behavior as we saw before. So this kind of network models and mechanisms can explain the differences that we see here. Very homophilic networks, PageRank actually does better, and I'll talk a little bit about PageRank as we follow up. But HITS does really badly. And this kind of backward forward pass, this kind of change in algorithm can change a lot from having a degree distribution that's already biased to one that's like extremely biased and suddenly pushes all minority nodes to the bottom of the hierarchy. Whereas in less homophilic networks, they're basically all doing the same, more or less mirroring whatever degree distribution bias we have started with. So this kind of work, until now, we had some empirical evidence that only completely disconnected communities would fare badly in this kind of algorithms. For example, in HITS, we didn't really know this kind of continuous relationship, this closed-form solution between community structure and bias in ranking algorithms that we're uncovering here. First of all, having some inequality in the degree distribution that leads to bias to begin with, and furthermore, any amount of homophily, there's a continuous relationship between homophily among communities and bias amplification in HITS. To quickly come back to PageRank, recent work, so we didn't know that much about PageRank in this kind of preferential attachment networks until basically 2 years ago. We didn't know, there was a conjecture that would say like, what is the PageRank distribution compared to in networks that follow preferential attachment. And recent work has shown like, well, if you have preferential attachment and a power law degree distribution, you also end up with a power law degree distribution in the PageRank score distribution, but with a much heavier tail. So it's just slightly different. Follow-up work showed also that, well, if you have these 2 communities, preferential attachment with 2 communities, which is the kind of model we have here, then you end up with a PageRank distribution with the same coefficient, meaning that you're actually supposed to be a little bit more fair. You might end up with different constants, and those different constants show, we see numerical and empirical evidence that amount to some bias in prior work as well as ours. And basically, we can do a very similar mean field analysis that shows that, well, you're going to inherit some bias from the degree distribution. It's less strong than a distributional result, and it's not going to be as bad as HITS. So the interesting part was to see that exactly this slight change between PageRank that does forward random walks and an algorithm that does backward forward walks would create a massive difference. We know exactly what the result would be on that and how much it can affect bias in the ranking itself. So I want to close off on a few future directions. Maybe taking a step back to the general project. What do we do about this? So we propose several interventions or adjustment on the random walk itself that can account for this kind of degree bias itself. You can think about this also in the space of you know, instead of doing a random walk, you can adjust it by a small counter bias to alleviate some of the issues that we see in the degree distribution. You can think about using more information than just the principal eigenvector of this network, so looking at the subspace helps a lot, and there's a question here like how much information do you need from the subspace in order to have a good ranking and also a more fair ranking as well. We have some empirical results on that. And more generally, we're thinking about what does this mean in the context of how these ranking algorithms would recommend like content, people's perception, as I shown in the first example of hiring, and in many other applications. of course, it'd be great to also generalize to other network models. We've done a little bit of that using continuous time branching processes, and I think there's a lot more work to be done there. And I'm going to close off here. Thank you so much, and this is our paper.
Thank you, Ana. I think we have time for one or two questions. If anyone has one in the audience. If not, I have a question I can ask. I don't know if you've thought at all about like how these algorithms maybe influence people's perceptions of homophily. I don't know if like you thought about homophily preference changing over time or anything like that in these models.
Yeah, I think that's a good question. There's some empirical work that has thought like different groups actually have different perceptions of homophily. So if you're a minority group, maybe you perceive yourself as like being actually smaller than you actually are, and things like that. And would love to incorporate this kind of insights. We haven't done it in this model, but I think it would be excellent to do so.
Thank you so much. And I think that's all we have for today. Thank you, Ana.